But anyway, okay, so let's get started. I will upload Lab 8 very soon because some of you finished Lab 7 already, but it doesn't mean that Lab 8 will be due before Lab 7, right? It will be due later. Okay, probably we're gonna have like until Lab 9, right? There might be a bonus Lab 10, but maybe not. Depends. Okay, and we will have 2 more homeworks. Okay, homework 4 and 5. Yeah. Okay, yeah, let's get started. Let's see what we're going to cover, what we covered in the previous lecture. So basically, in the previous lecture, we kind of officially going into the regime of digital communication. So we talk about pulse modulation. So basically, pulse modulation meaning that we're going to use samples of signal to modify parameters of a rectangular pulse train, right? So like this, right? So this basically means that we use the magnitude to represent a signal, right? So it's called pulse amplitude modulation, right? You can find this is very similar to what? To kind of like amplitude modulation in the analog communication, right? So now, basically, what we're going to transmit is kind of all these pulses, but the difference here is that all of them will be quantized, right? They're going to be in a fixed level. So this value will not be all the real numbers, right? Now the question is how to transmit the value here, right? For example, we can transmit them directly using a rectangle pulse like this, right? But here it's flat, okay? So this is one way. And the other way is that, okay, so we're going to use some digits to represent each of the pulse and then just transmit those binary digits, right? So those basically is the idea for this. And also, we can have some other kind of modulation approach, right? For example, the width of a pulse can represent the information, or the location of the pulse can represent the information, right? We don't cover details of that. I have no idea where we use that in 5G or Wi-Fi. So, yeah, just as long as you know that, we're going to be fine. And there's some advantage and disadvantage of it. You can take a look at that. So we cover that exactly in the class. And one advantage of the pulse modulation is that now, instead of transmitting the whole continuous signal, then we just transmit all the pulses here, right? Then we can do the time division multiplexing, right? At the same time, we can transmit 2 signals instead of 1, so that can be a very big advantage of it. Okay, and then so we introduce another very important pulse modulation approach. It's called PCM. So basically, the PCM meaning that, okay, so it's like exactly what I said before for PAM, right? So basically here, we quantize the signal into levels. Here we have 4 digits, so therefore we have like 16 levels, right? And then we just transmit all of those kind of numbers, right? So now instead of transmit the real numbers here, because we have a one-to-one mapping between this number and our 4 digit, right? Then we can just transmit this 4 digit, right? Then it's kind of a coding, right? So we code a value, a real integer here, into all of this bit, right? It's called bit encoder, right? Then we just need to transmit the binary bit, right? How to transmit it? Then we have so many ways, right? So we're going to cover many ways to transmit all of those bits. Right here is a simple example. Like I say, we just transmit, okay. If it's 1, we transmit a rectangle pulse. If it's 0, we transmit nothing. If 1 is another rectangle pulse, and so on, right? So this, yeah, it's just now we can see. So this is the only difference between the digital and the analog communication here, right? So basically now those are the signal we're transmitting, not the GT anymore, right? Okay, and one big disadvantage of PCM is that, so let's assume that for the PCM, we just transmit exactly what we said in the last slide, right? So basically, we're going to transmit the 0, 1 using the rectangle pulse, okay? And here we can say that, so the bit rate is 21B bits per second, where bit is, capital B is the bandwidth of the signal, right? And if we compare this formula with what we have learned before, we can see that because now we have only 2 levels, right, 0 and 1, okay? So these 2 basically can be interpreted as that 2, right? And this NB would be the bandwidth of the signal, right? So which is n times bigger than if we don't use a PCM, right? If we think it carefully, or not carefully, if we think it again, intuitively it could be mean that, right? So basically, let's say if we just transmit those levels directly using a rectangle pulse as wide as this, right? So there will be a bunch of these rectangle pulse like this big, right? And then the bandwidth is like, so 1 over this will be your bandwidth, more or less, right? But now, because we decompose it into 4 digits and like into 4 small waveforms here, right? So each waveform would be like 4 times shorter. Then the bandwidth would be like n times bigger, right? So that's maybe an intuitive way to understand that. So yeah, it looks very complicated, but it's really not that hard. So it's just how we interpret it. Okay, and then we introduce you 2 applications of PCM. So both of them are very old kind of applications, and probably don't use that anymore. So one is called plain old telephone service, or POT, and the other one is a compact disk, or CD, right? So yeah, we give you a little bit details on that in the lecture notes. You can take a look. Okay, and then we cover a bunch of advantages of digital communication compared to the analog communication. So more or less, conceptually, the only difference here is that instead of transmitting whatever real numbers, now we're transmitting 0 and 1s, right? And then if we use 0 and 1, there are a lot of advantages here. Okay, so yeah, we don't go over that anymore. So we go over that one by one in the last lecture. So yeah, we're going to talk about this lecture. So basically, the first topic of this lecture is that, so yeah, those are the 2 topics of today's lecture. So the first one is the desirable properties for digital communication, right? It's like, okay, so what do we want from the digital communication, right? What are the desirable properties of it? And then we'll introduce a very common and basic modulation scheme. It's called line encoding. So that's a modulation scheme that we use for what? The baseband communication. Okay, so we'll see the meaning of it. Okay, so the 2 most important properties of the digital communication are these 2 things, right? So there's a trade-off between the spectral efficiency and the energy efficiency, right? Spectral efficiency, so we're going to introduce that in much detail later, probably in the next class or maybe a few lectures later. So basically, spectral efficiency meaning that, so we normalize the transmission rate by time and by bandwidth, right? So basically means that, so how many bits we can transmit per second per hertz? Okay, does that make sense? Sort of, right? Because now, when we talk about communication, we mainly care about 2 dimensions, right? One dimension is time, so the other dimension is frequency, right? It's kind of agreed, right? We can allocate information, okay, at this time and at this frequency, right? So, and our unit is per second per hertz, okay? And we want this one to be as big as possible, okay? And the other one is energy efficiency. So basically, normally we measure that in terms of a signal-to-noise ratio, right? So basically, what we want is that, so we don't want, yeah, of course we want high SNR, but normally that is, we need to cost lots of energy for it, right? So basically, normally lower SNR meaning it's more energy efficient, right? And clearly there's a trade-off between energy efficiency and spectral efficiency, right? So if you want a higher spectral efficiency, maybe you want to get more energy, then it's a worse energy efficiency. Okay, so we're going to investigate that later in this class. Okay, and the other thing is that the synchronization ability. Okay, so what we want is that we want to extract the timing information from the modulated waveform, okay, to synchronize the information. Okay, and yeah, and this can be challenging, right? So we're gonna tell you why in a short time. So, and the other thing is design of or analyze of the power spectral efficiency, or PSD. Okay, so for digital communication, this is one of the most important parameter to look at, right? For one of the reasons we look at PSD is that, oh, by the way, who still remember PSD? So we talked about that before. Yeah, very good, right? So that's a Fourier transform of the what? The autocorrelation function, right? And the integral of the PSD will give you the power of the signal, okay? And this basically will give you how the signal will look at in the frequency domain, right? Normally, the signal that we transmitted is random signal, right? The randomness can come from many, many sources, right? For example, the source information can be random, right? And then we add some random noise on this, maybe multiply a random channel coefficient and so on, right? The signal are random, right? If a signal is random, then it's kind of complicated to analyze, right? So one way to look at that is just to analyze the power spectral efficiency because it's kind of expectation or average, right? So that's easy to look at, okay? Yeah, and also we generally don't want a DC component in that because, because the DC component does not carry any information, right? And also the other thing is that we need to look at what's the channel look like, right? And then design the power spectral efficiency to make signal that can pass through the channel, right? Normally, if the frequency is very low, then it's not easy to radiate. Okay, and the other thing is the error detection and the correction capability. We kind of mentioned that before. So one big advantage of the digital communication is that it is capable to detect and correct errors, right? For example, let's say if we transmit, for example, if the information is a 1, and then if we transmit 1 like 3 times, then there's a lower chance that we can have an error, right? Because we transmit 3 times, okay? And then you can recover the signal perfectly, right? Okay, and but how to design this error detection and the error correction approach is called coding, right? Or the channel coding, right? There are many kind of ways to design that, and it's extremely important in the current communication technology and standard. Okay, and the last thing that we want is called transparency. So basically, what we want is that if we don't have the noise, then we should be possible to recover the data without ambiguity from the transmitted waveform, right? So kind of, okay, if there's no noise, no distortion, we should be able to recover the signal exactly, right? So those are kind of a few desired properties that we want. And from now, we're going to cover specific modulation scheme for the digital communication. Right, so this is a figure that we introduced actually in lecture 1 for the digital modem. Right, so basically those are the procedures, right? So yeah, this encoding basically means the channel encoding, right? So we encode our input bit into some other bit, right? So and then we have this. We're gonna explain that in much later. Okay, and the important thing here is that we have a pulse shaping here, so we're going to explain what that means, right? So probably we're not going to cover how we're going to design the optimal pulse shaping. If you're interested, you can take a look at the book. So what we're going to focus on is the modulation, okay? So yeah, pulse shaping basically is that meaning that what kind of pulse we're going to use, right? For example, we introduce this like if it's a 1, then we'll just transmit a rectangle. If it's 0, transmit nothing. That's a pulse. Right, this rectangle and 0 are kind of the pulses that we use, right? The pulse will determine many things, right? It will determine the bandwidth of the transmit signal and many other things, right? But think about this, right? Once the pulse is determined, right? So what we're transmitting is just a bunch of this rectangle or nothing, rectangle or nothing, right? And those are what? Those are analog signals. They're not digital anymore, right? There are continuous time analog signals. And then how can we transmit it? Am I clear? Yeah, maybe I'm going too fast, right? So after the pulse shaping, so what we're going to have is a bunch of, yeah, maybe we can look at that here. Yeah. So yeah, after the pulse shaping, right? Those are what we transmit, right? They're just continuous time signal, right? So here we have all 1s, and here we have 0, and here we have all 1, we have 0, and so on, right? Those are analog signals, right? Do you agree? Right? Before, we just have this kind of analog signal, but now it just look a bit nicer, right? And then all the modulation scheme that we used before can be used here. We can use DSB-SC or DSB no SC, right? Or whatever, right? Or like VSB, SSB, or USB, or LSB. Hopefully still remember those, QAM, right? We can use everything that we learned so far to transmit those, right? Yeah, without big difference. Okay, so now we know how to transmit those already. Is that right? Okay, so we don't need to really worry about how to move the signal to the subcarrier and then to transmit it, right? The only thing we worry about is, okay, so now the signal shape is like this, not like arbitrary anymore, right? So how can we, demodulate it, right? How can we, recover the 0 and 1s, right? So those are what we're going to focus on, right? How to move it into a higher subcarrier, and then how to transmit it over the air. So that has been already covered. That clear? Right. So then we care about, from now on, we care about baseband signal, right? Of course, if we're going to use something different for the high band, yeah, we'll say that explicitly, right? But now we just care the baseband signal. Okay? Is that clear? Logic? Okay. Okay, so now let's talk about the line coding. So normally line coding is mainly designed for baseband. Okay. And also normally it's binary signals which only transmit 0 and 1s. Okay. So basically what we do is as follows. So we only transmit 0 and 1s, right? For 0, we need to map it to some signal, analog signal that we're going to transmit, right? So we call that as 0t. And then if it's 1, then we call this as 1t, okay? So this is, that's it. Okay, so now we need to look at, okay, so what kind of ST and S0t and S1t makes sense, right? So as we said before, so yeah, we give you something like this rectangle shape, right? So actually there are like a few more options here. So we have 2 options. Normally in practice, yeah, there are more than that for sure, right? So those are kind of very typical things that we use. So one is called non-return to 0. Non-return to 0 shape. So we'll call that NRZ. And the other one is called return to 0, right? No N anymore. Called return to 0, or RZ, or somebody calls this RTZ, return to 0. Okay, who heard of that before? Oh, good. Not many. Yeah, the concept is very easy, so let's see. What does that mean exactly? So let's see the first one, okay? NRZ. Okay, so never return to 0 basically means that during the symbol time, so we never return to 0, okay? Like this, for example, let's say our pulse shape is like this, so the duration of this is our symbol time. So let's see what symbol did I use for the symbol time. Use T here. So let's see here, this T is symbol time, okay? And then, so this can represent something, right? So from 0 to T, so that is the duration of 1 bit. So it never returns to 0. Okay, so that's why it's called NRZ, not return to 0. Okay, so that's one example. So the signal are not required to return to 0. Okay, for NRZ we have a few cases. So one is called unipolar NRZ. Yeah, for unipolar NRZ, so basically it means that we only have one amplitude, right? So we only have one amplitude. Meaning that if it's a 1, for example, if it's 1, then we transmit something. If it's 0, transmit nothing. Just have one amplitude, okay? Or vice versa. So yeah, let's see an example of each of them. So we consider information sequence. Let's consider an information sequence like this. So we denote that as a U equals to 1, 1, 0, 1, 0, right? So this is what we transmit. So let's see what do we mean by unicolor NRZ code, okay? So in this case, so what we do is as follows. So basically, let's assume if it's a 1, then we transmit this waveform, okay? So let's say the magnitude is A, right? So this is what we transmit for 1. And then if it's 0, then we transmit nothing, right? That's why it's called unipolar. All right, so yeah, let's see. So if the transmitted sequence is like this, then so what we do is as follows. So basically, the first one is a 1. Then this is what we transmit. Okay, and the second one is also a 1. Then we transmit this again, right? And then the third one is 0. Then we don't transmit anything, 3t. And then we transmit 1 again. And then we don't transmit anything. And that's it, right? So this is called unipolar NRZ. All right? This is how we transmit it. Okay, and you can see this is an analog signal, right? So we can do whatever we want on this. All right, very good. Okay, so now it's a very simple one, right, that you may ever imagine. So now we can see, so based on the desired property we talked about in the beginning of the class, so what do you think the problem of it? Right? Is there any undesired property of it? Well, let me remind you a little bit, right? For this kind of thing, so as we said, right, we don't want DC component, right? The DC component carry no information and costs energy, right? How about for this one? Is there a DC component for this one? Of course, right? We don't have anything negative. We only have something positive, right? Then there will be definitely a DC component here, right? That's not good. So DC component. Okay, so this is a problem, right? That's not very good. And there are any other problems? ER student mentioned this last time, right? So for this kind of thing, it's very hard to synchronize. Okay, the synchronization will not be easy. Okay, so that can be a lot. We have a lot of problems, right? The reason is that if we transmit a long 1 or long 0, especially long 0, then how can we synchronize, right? We have no idea where the signal starts, right? If the signal starts from a bunch of 0, then there's definitely no way to tell where to start, right? Right? We have a synchronization issue. Okay. Okay. So now let's see how can we solve the problem, right? So unipolar is not good enough for this. So how about? So an easy way to fix the first one is that okay, how about we just move it a little bit, right? Move it down a little bit to get rid of DC component. Does that make sense? Right? For example, normally, in our transmitted signal, so the probability of transmit 1, 0, they're equal. Why is that? They may not be equal, right? But if they don't equal, can make it equal, right? So that's called scrambling. So, but let's assume that normally it's a valid assumption, right? The source information are equally distributed between 0 and 1, meaning that the probability of the signal is 1 is 0, is half, and then the probability of signal is 1 is a half, right? So that's a valid assumption. Okay, because of that, we can use so-called bipolar NRZ. Okay, so for the bipolar NRZ, so the idea is it's almost identical. The only difference here is that, okay, if it's a 1, we transmit like that, we transmit something like that. If it's a 0, then we transmit the negation of it, right? So basically it means that if it's a 1, we transmit that. Okay, and if it's 0, we transmit this. Okay, and now let's see how it looks like. So we're going to repeat this here. So basically, in this case, we're going to have 2 1s, and then we have a 0, right? Let's mark it, it's 1, 1, 0, 1, 0, right? And for 0, it's like this. Then we'll transmit 1 again, and then 0 again, right? We have 2t, 3t, 4t, and 5t here, and the magnitude here is a, and here is minus a, right? So this is bipolar NRZ. Okay, so obviously one advantage is that no DC component. And here, of course, we assume that ones and zeros are equally likely. Yeah, for equally, how many L I should have? 1 or 2? 2, right? For equally? Q, U, A. Right, I have 2L, right? Yeah. Equally likely. Okay. Yeah, very good. Okay, so the DC component, this problem can be solved, right? How about synchronization issue? Do we have synchronization issue? Yeah, we still have it, right? So if we have a very long time transmit 1 or very long time transmit 0, right? So it's kind of hard to synchronize, right? We still have synchronization issue. Issue remains. Okay, so that's not very good. Okay, so basically, in order to get rid of the synchronization issue, we need to have something different, right? We need to make a signal change all the time, and then we can see the pattern and see where to start. Okay, so if I have long time of 1 and long time of 0, that's not good, right? So in order to deal with that, so we can design something that is a little bit more smarter, right? How can we design it? Under the under the realm of NRZ, right? So basically, we don't want, let's say, if we transmit all the ones, right? It's all flat here, right? If we transmit 0, it's all flat here, right? That's not what we want. We want the signal to be changing, right? How can we make sure the signal to be changing? So can you tell me, can you design a pulse shape? Yeah. Yeah, that's called scrambling. Yeah, that's very nice, right? That solve the problem from here, right? We don't transmit 1, 1, 0, 1, 0 anymore, right? We can add some bit into it, some deterministic bit, and then we can decode it at the receiver. Is that what I mean? Yeah, that's a very good solution. Yeah, that can do it. But let's say, can we do it from here, right? If we don't change it, we design a different shape of it. So can we achieve something similar? Yes. Very good, right? Cosine wave is a good option. Yeah, and actually we're going to talk about that probably 4 or 5 lectures later. Okay, but we're going to do something very similar, but it's simpler than cosine, right? It's almost cosine. So basically, what we design is something like this. It's almost cosine, but something like that. Okay, still square. Okay. So basically, we have a here, we have minus a here, and then here's 0, here's t half, here's t, right? So this represents a 1, and the minus of this represents a 0. Okay, then you can see the signal will always changing, right? Okay, so I have a name for it. It's called Manchester NRZ. It's called Manchester NRZ, and this is the basic pulse. Right, so basically, from the syllabus or from the book, you can see, or from what we discovered before, you will see pulse shaping, this word all the time, right? The pulse shaping meaning exactly how we design this pulse. Okay, because different pulse will give us different frequency response of the signal, will give us different power spectral density, right? But here we don't talk about the only, okay, so how to maximize the pulse exactly, right? But I just give you a bunch of different options, right? And see how different pulse will be how different pulses will behave. Okay. Okay. So now let's see how we can draw this figure again using this pulse, right? So basically, in this case, what we have is as follows. So basically, the first one is a 1, right? And here's 0, here's t. And the second one is another 1. Oh, it's too wide. Right, this is 1, this is another 1. And then it's 0, right? 0 is a negation of it. So basically, this is 0. And we have 1 again, right? Yeah, let's mark it. It's 2t here. Here's 3t. Here is 4t. And then the last one is a 0 again, right? So do a negation of it. Yeah, here's 5t. I have a 1, 1 here. And this one is 0. This one is 1. Last one is 0, right? So this is what we transmit. And you can see the signal changing all the time, right? So we don't have a long level that doesn't change anything, right? So this seems to solve the problem, okay? So which is good. Okay, and now let's see. Okay, so far, I mean, this looks pretty good. But what are the problems for this one? Right? So compared to this one or this one, right? So what are the problems? Or, what are the worst property of this compared to that? Right? See, the only difference here is that now this becomes narrower, right? So we have a t-half. This is still a rectangle, right? But with a t-half for the time duration here, right? And then this guy is another t-half duration, right? So in the time domain, for like 1 pulse, the time duration is shorter, right? Basically means that it requires more bandwidth, right? Because in the time domain, it's changing very fast. It's twice as fast as this or this, right? It basically means that it occupies more bandwidth, right? So the problem of it, this is that, so we need 2 times the bandwidth compared to the the other 2, right? So that is not very good. Or if we don't change the bandwidth, we have to make this guy wider, right? Then it means half the bit rate, right? So which is not as efficient as those. Okay. Yeah. Any questions? Okay. So now let's talk about the second one, the return to 0 code, or RZ or RTZ. Okay, second, return to 0 RZ or RTZ. Okay, so for this one, from the name, you can see, so basically it means that it will return to 0 during the symbol period, right? So again, we have a few cases here. So the first one is, again, the unipolar. RZ, okay? So basically, it means as follows. So for 1, so this is what we transmit. We have 0 here, and then here's t-half, here's t, right? So it returns to 0 during 1 symbol period, right? Okay, and then, so if we use our original example, and we can see how it looks like is basically like this, right? So we have, again, it's unipolar, basically means that it's 1 amplitude, right? If it's 0, we just transmit 0. Okay, so this is for 1, right? And then we have another one, this t-half, right? And then we're going to have 0. 0 basically means 0. And then another one, 4t, and then another 0. Right, so this is what we transmit. We have 1, 1, 0, 1, 0. Okay, so this is for unipolar RZ. Okay, and similarly, again, we have bipolar RZ, right? Again, the only difference is here. The only difference here is that, so we're going to, the magnitude is A, we're going to use the negation of it to transmit a 0, right? So if it's a bipolar, then just look at here. The only difference here is that when it's a 0, then, let's see, we transmit this, right? And when 0, then we transmit this instead of nothing, right? The red part together with the black part would be what we do for the bipolar case. That clear? Right? Yeah, this is basically the basic concept of the line coding. Okay. So next, we're going to the main topic here, right? So yeah, I think we only have like maybe 2 or 3 topics left in this class, right? This is one of the most important topic, right? It's called, so we're going to characterize the power spectral density of this kind of signal, right? Let's see how we can do that. All right, so power spectral density of line coding. Okay, let's see how can we compute that. So before computing the power spectral density, we need to write down, so what is the transmitted signal look like, right? So basically, the transmitted signal look like as follows, right? So basically what we have is here, let's say our transmit signal is AK, right? And then we need to use a pulse, right? So like this, we need to use this to modulate on the AK, right? Now, in our case, AK is just 1 and minus 1, right? In practice, you know, if it's not binary, so AK can be whatever, right? It doesn't have to be 0 and 1, but in our case, it doesn't have to be like, yeah, 0 and 1 or binary. Okay, but in our case, so let's assume that we use AK, multiply the pulse shape, and we denote the pulse shape as P here, T minus KT. I use TB to denote, because now we may focus on the binary case, so we assume duration of each bit as TB, right? So this is our transmitted signal. Okay, so let's be clear on this definition. So AK here is not UK, right? Remember that. So AK here is not U, right? We use U to represent the original information, but AK to represent this information. Okay, either it's a -1 or either it's +1 or -1 or whatever. The magnitude of this, right? So what we multiply on this pulse, right? For example, if it's for a bipolar NRZ, right? So basically, we map if it's for let's say bipolar NRZ, right? So UK, let's say U is basically 0 and 1, but let me see how can I write it. U is 0 and 1, and let's say A is like -1 and 1, right? We map 0 to -1 and 1 to just 1. Okay, this is what I mean. Magnitude of the pulse. Okay, I mean the value of the pulse. Okay, so basically that means the line code, the line code amplitude, right? And this this P this PT is the general pulse shape. Okay, and this TB is our bit duration. So now basically we want to characterize the PSD of it, right? How can we compute it? Right, so before computing PSD, yeah, let's see another representation of it, right? So basically, so this equals to what? Right, so basically we can rewrite this as follows. So we can take this PT out, right? Because if you see this kind of, so I've seen this kind of form many times, right? The kind of a train here, right? So basically what we do here is that, so we let that we can see this O equals to the PT convolutes a summation of impulse train. That makes sense? Right, because PT convolutes delta will give you this, right? So we can rewrite that in terms of that. Okay, then why do we want to write it? Right, because that can make our life easier, right? So we can see, so here, so this PT, we can take this PT out, right? So if we want, to compute the power spectral density of it, then we may want to compute that. We have to compute that the frequency, right, in the frequency domain, right? So if we have something like that, then we can take this completely out, right? So basically, the spectral efficiency, the spectral, the power spectral density of this guy will be equals to what? The power spectral density, this guy squared, right? Then multiply the power spectral density of this, right? So basically, the power spectral density of this, let's denote this signal as x of t. Okay, then basically, the power spectral density of y will be equal to this guy multiply the power spectral density of x. Okay. And this is the PSD of xt. And this is what we want to compute, the PSD of yt. Right? So did we cover that before, this formula? So who have seen this formula before? So if I didn't cover it, then I'll just tell you, okay? So basically, yeah, maybe let's draw the system diagram, right? So if I represent our signal in this way, so basically, yeah, because we have a convolution here, right? Then we can understand this as a linear system, right? Linear time invariant system. So basically, in such kind of system, let's assume our input is x of t. Okay, so let's say our input is x of t, and our x of t is nothing but a bunch of impulse, right? Right, for example, here might be a minus 1, a0, a1, a2, and so on, right? And then we pass this signal via a linear filter, which is PT, or capital PF, if we think that in the frequency domain, right? That is our pulse shaping filter. Right, and then we have our output, which is yt. Right, if you consider such a kind of linear system, then the relation between the power spectral density between the output and the input is like this. Okay, so the PSD of the output equals to the unit impulse response of the signal of the filter absolute value squared multiply the PSD of the input. Okay, so this is a given. Very good. Questions? Okay, so now our goal is to compute using this formula to compute this guy. Okay, and this is known, right? Because there is whatever RZ and RZ, we can compute it using Fourier transform, right? And this is kind of troublesome. Okay, so as long as we can compute that, and then we can compute this, right? Then our focus is how to compute that. Okay, the power spectral density of x of t. Oh, we're out of time already. Yeah, I'll just write one more line, and then we're done. So basically, we're going to compute that in the next class in very detail. Or you can think how we can compute it, right? So yeah, we cover how to compute the power spectral density already, right? So how can we compute the power spectral density of x of f? Right? We say computing that in the power domain is very hard, right? So if you forgot, just take a look at our note, right? So the reason because of definition of it, right? And so what we can do is that we know the Fourier transform. So the inverse Fourier transform of it is the autocorrelation function. Oh. It's the autocorrelation function of x tau. Okay, so this is not so hard to compute, right? So if we compute this, and then we do the Fourier transform, we can get that, right? Then now the goal is to compute this guy, right? And how can we compute that? Using the definition here, right? So this equals to this. T goes to infinity, and then we have 1 over t here, and then we do the integral of this guy. And here inside is xt. It's autocorrelation, right? Xt multiply a shifted version, delayed version of itself, right? And then we can compute xr r tau, right? And you can see, is that hard to compute this guy, right? Ignore, this part. The key is to compute this guy, right? And remember now, our x of t is just a bunch of delta signals, right? If we shift it a little bit, it'll give you 0, right? Only at a certain point that's not 0, okay? So basically computing that is not very hard. It's pretty easy, as we're going to see in the next lecture, okay? So yeah, that'll be it for today. Thank you.